Today we are going to discuss about moments of a charge distribution. We know that an atom or a molecule consists of some electric charges which occupy a small volume. This volume can be around a few cubic angstrom. We are usually interested in electric field outside that volume. So, by which we means that we will be interested in a rather complicated charge distribution. We shall particularly concern with field far away from the source. That is, if we have a source and let's call a point P which is far away from the source, we are interested in this point. How much far away is enough? That depends upon the size of the source itself. To understand this concept better, let us take this system. Here we have a charge distribution here. Let's call this charge distribution rho. This charge distribution is dependent upon space. So, and we want to know the potential at point A due to this complicated charge distribution. To understand this, let us consider a small volume element dv prime here. dv prime is located at a distance r prime from the origin, and let us call this point M, and the vector joining point M and A will be our capital R vector. And let me change color here. So okay, so and the vector joining O and A will be small r vector. So the potential at point A due to this small volume element will be given by d phi, for the notation is equal to 1 over 4 pi epsilon naught into rho x prime y prime z prime dv prime upon r, where this is the charge distribution at point M. Charge distribution at point M. And to find the whole potential dependence due to this charge distribution at point A, we will be integrating around the volume. So our phi A will be given by 1 upon 4 pi epsilon naught integration rho x prime y prime z prime. And also we have a vector identity between these three objects, which is small r vector is equal to capital R vector plus r prime vector, and r vector can be written as minus r prime. Now r scalar, the magnitude will be given as r square plus r prime square minus 2r r prime cosine of theta raised to power half, where theta is the angle between OA and OM. This is our angle theta. So now all we need to do is insert this value in the above equation phi A. So if we insert this, we'll get, so if we insert the value of r in phi A, we'll be getting this result, and this whole thing can also be represented in this way. But now we will be solving this quantity to simplify our lives. So now r square plus r prime square minus 2r r prime cosine theta raised to power minus half. If we take r common, we will be having 1 upon r 1 plus r prime square upon r square minus 2r prime upon r cosine theta raised to power half. Okay, we know that we are interested in at points far away from our source. So r prime is much less than r. That is, r prime upon r is less than, very less than 1. So that we can call this object delta. Now delta is less than 1. Here we can use now binomial expansion. So now 1 plus delta to the power half minus half can be written as 1 minus delta over 2 plus 3 delta square over 8 plus and so on. So those who don't know about binomial expansion, I have written this formula here. Okay, all we need to do is insert the value of delta in this equation, and this is our delta. If we do this, we'll have this thing, and this is our delta here, and this is our equation, and we will be opening it using binomial expansion. After this, we'll have this thing and this go on, but then now we need to separate terms from r and r prime square upon r square, comma, r prime cube upon r cube, and after that we'll have. So now all we need to do is insert this value that we have calculated in our previous equation, which is this. Let's do this. Phi a is equal to 1 upon 4 pi epsilon naught, and this was our thing, rho which is under integration dv prime upon r, and this is equal to 1 upon 4 pi epsilon naught 1 upon r integration rho dv prime plus 1 upon r square r prime cosine theta dv prime plus dv prime into rho plus so on. These things, these things, these are called moments of the distribution, called moments of distribution. These things, this one, this one. The first one, it is called monopole distribution. The basically this quantity is just that we use in Coulomb's law. Phi a is equal to, that is 1 upon 4 pi epsilon naught rho dv prime upon r. This is just as Coulomb law. And the second term, this term, it is called the dipole moment. Called dipole moment. And the third one, it is called quadrupole moment. So now let us write this in a simple form. This thing. So let's just clarify our notation to simpler terms. K0 is equal to rho dv prime. This is simply our total charge distribution, and K1 is equal to r prime cosine theta rho dv prime. This tells us about dipole moment, and so on for K3 and K2, K4. So now phi a can be written in the form 1 upon 4 pi epsilon naught K0 upon r plus K1 upon r square plus K2 upon r cube, and so on. This power series that we have now calculated, it is called multipole expansion. Multipole expansion. So let's ask how we will be able to know what is the behavior of charge distribution at larger distances. For that, all we need to do is calculate for these things K0, rho dv prime, K1 and K2. And we will see for the first term which we are getting non-zero, K0, K1, K2. Whatever the first term that we will get non-zero. If we get K, for example, if we get K0 is equal to 0 and K1 is equal to something but not 0, then we will say that at large distances the distribution will behave as a dipole distribution. And if we get k2 is equal to something rather than 0, where k1 is 0, then we will say the distribution have a quadrupole moment at large distances. So now, so let's ask how we will be able to know what is the behavior of charge distribution at larger distances. For that, all we need to do is calculate for these things k0, rho dv prime, k1 and k2. And we will see for the first term which we are getting non-zero, k0, k1, k2. Whatever the first term that we will get non-zero. If we get k, for example, if we get k0 is equal to 0 and k1 is equal to something but not 0, then we will say that at large distances the distribution will behave as a dipole distribution. And if we get k2 is equal to something rather than 0, where k1 is 0, then we will say the distribution have a quadrupole moment at large distances. So now, and in this way we'll calculate moment of a charge distribution. And so this is it. If you have any doubt, please let me know.